there are different ways to minimize switching losses. So one of the methods is to use snubber circuits. Let's see, where is our snubber chapter? Right there. Okay, so snubber is an additional circuit that you would connect around a switch, whose job is to reduce switching loss. Right. So where's my, okay, right here. Yeah, so understand that snubber will for sure reduce switching loss, right? But that doesn't mean that it's always going to reduce the entire converter loss. In fact, if you're not careful, you can end up increasing total loss of the converter. But if you don't if you don't choose the components of the snubber properly, right? So in general, total loss for a converter is the static loss, switching loss, and others, right? That's before snubber, and after snubber is going to be the same thing, right? So this is before snubber, you don't have any snubber loss here, right? And then after snubber, so there's no, so I should say P snub is 0, right? Because you don't have snubber. So that's before snubber. After snubber, of course, you're gonna have plus P snub, right? And this is what I call P others, right? And so after you put snubber, then for sure that the switching loss is going to decrease for sure. That's guaranteed. Okay. What is not guaranteed is that what you need to be careful of is that the total loss right there, it could go up or down. It could be bigger than before, or it could be less than before, depending on how you select components in the snubber. So therefore, this is very important to to size. And this is what we're going to be learning in this chapter, is to be able to size a snubber properly. Okay. All right. So before we learn about snubber, which is one of our solutions, we need to understand the problem, right? Once we understand the problem, then we can start looking at the solution. So what is the problem? Switching loss, right? And in particular, the problem is the fact that switching waveforms are overlapping. So we're going to look at that first before we look more into snubber. All right, so in terms of the type of snubbers, there are two different types, turn off and turn on. Right? So turn off means that the snubber is being used, or the circuit is being used to minimize turn off switching loss, only the turn off transition. Whereas turn on, as you already can guess, it's being used to minimize switching loss that's coming from the turn on transition, right? The way we minimize the losses, the switching losses, is by reshaping the trajectory, right? Now we already know what trajectory means, right? When I say trajectory, it means switching trajectory. So by reshaping the switching trajectory, we should be able to minimize the loss. For example, if the trajectory starts from this type of trajectory, right? With snubber, you could reshape into this kind of trajectory, right? So you can see the area becomes less by reshaping the trajectory, right? And as you learn, the area under the switching trajectory corresponds to loss, right? It doesn't tell us how much, but gives a good indicator of relative loss, right? Coming from the switching. Okay. And to explain the concept of snubber, I'm going to use the first type, which is the turn off snubber, right? I'm not going to do the turn on, even though the turn on snubber is also covered in this chapter. I will ask you to review that turn on snubber yourself, right? If you understand how turn off snubber works, then you should be able to understand turn on snubber. Another reason is that from practical point of view, turn off snubber is being used a lot more than turn on. Okay? Has to do with spike, voltage spike that is caused by a switch turning off, right? And most common way to reduce that leakage spike, reduce the spike or eliminate the spike is by using turn off snubber, right? I'll talk more about that. We'll see if you have the time to do that today, right? So let's look at turn off snubber. Okay, let's do before snubber, and I'm going to use a very simple circuit to explain how snubber works. Okay, so this is without snubber. Right? So I have this simple circuit where I have a transistor that is working as a switch, and then I have this inductive load that heavily inductive, so that I could model the load current as current source. Right? And then because this is a current source, highly inductive, therefore if the switch is off, we better have a path for this current to flow, right? That's why you have this freewheeling diode. Just in case this switch is off, this current source will still have a path for it to flow, right? Otherwise, imagine if this is inductor, you turn off the switch, if there's no path, then the inductor will be pissed and you're gonna get so much high voltage across that switch. And in turn, that will damage that switch, okay? So a simple circuit to hopefully understand the operation of a snubber. Assumption in terms of switching transitions of the switch, I should have it right here somewhere. Okay, yes. The switch current and voltage change linearly, right? So we're gonna assume that when the switch voltage or current changes during the transition, it will change linearly, right? And also gradually, right? So there's no jump, there's no step in the change, okay? Both for turn on and turn off. So as you can see from here, you see this, both are linear change. Okay, that's the first assumption. Excuse me. Secondly, again, I already mentioned the second one is that the load is inductive, so therefore it's going to require freewheeling diode. Right? Now, let's see, supply voltage is Vs, load voltage is VL, that's voltage across the load, right? That's VL, polarity that way. And switch voltage VQ, also plus minus that way. Okay, current, we have three different currents. We have load current right there, IL, we have diode current ID, and we have switch current IQ, right? So based on this, I should be able to write KVL and KCL, right? KVL states that supply voltage should be equal to VL, the load voltage plus the switch voltage, right there. Okay, and then KCL should be equal to, KCL should give us load current, IL equals to IQ plus ID, right? And if you look at that node. Any question on this KCL, KVL first? Any question on this? That should be easy to understand, right? Any questions? Okay. If not, okay. So let's see what happens when we have a turn off transition. Let me erase this first. So I'm going to focus on turn off only, right here. That's what I'm going to focus on. I should not use that one. My bad. Okay. All right. So turn off transition only. Okay. Hang on a second. So here I have, if you can see from this turn off transition right there, you can see that I have voltage. We can see that the voltage changes first before current, right? As the voltage rises, because it's turning off, right? current stays the same, and then once voltage is reaching the peak value, which is Vs right there, that's when current start to come down. Okay, how is this? Why is this? Right? That's probably what goes in your head. You know, why is the transition goes like this? Why is it that voltage start to change first, and why is it that current will have to wait, right, until it can come down? Well, first of all, again, by looking at this KVL, right, I know that this diode can only conduct if its voltage is equal to 0. Do you agree? Or in other words, if this voltage is positive, if diode voltage, which is VL, is positive that way, right, plus minus that way, if it's positive, then what's going to happen with the diode? Is it forward biased or reverse biased? Which one? Anybody?
Forward.
Reverse.
Right?
Reverse bias, right?
Oh, reverse.
Right, because the diode is more, sorry, the cathode is more positive than anode, right? So therefore it's going to be reversed. So anytime VL is positive, that means this diode cannot conduct at all, right? So the only time this diode can conduct is when its voltage is equal to 0, right? Or negative voltage, but we would never get negative voltage, you'll see. Okay, so if you look at this transition right here, right, as the voltage across the switch, this voltage right there, is increasing, is rising, see that? So the voltage is initially 0 because it's conducting, right? Initially 0 volt here across the switch, but then when it's turning off, it starts to go up, right, linearly. That's the assumption. As this voltage goes up, right, following this KVL, right, as VQ goes up, what happens with VL?
Goes down.
It goes down, right? So before Vs is equal to VL plus 0, right? Because before the turn off, BQ is equal to 0. It's conducting, right? But as you are turning off the switch, this voltage from VQ goes from 0, just like you see here, goes from 0, and then start to rise, right? And this goes up higher, and because of that, because the Vs is constant, by KVL, VL has to go down, right? But even though VL is going down, it's still positive, right? If let's say this is 12 volts input, right? And the switch voltage now rises to 1 volt. Right? Voltage across VL must be 11 volt. And that's still positive, right? 11 volt right here. It's still positive. Positive means reverse bias, right? That means as long as VQ is less than 12, VL will always be positive, right? As long as VQ is less than Vs, right? Voltage across the diode must be positive, therefore reverse bias. If it's reverse bias, then based on KCL, ID must be equal to 0. So therefore IL must be equal to IQ, right? Because ID is equal to 0 amps, right? So that's why if you look at this picture right here, right, as long as VQ, as long as voltage across the switch is rising and the values below 12 below Vs, right, you won't have any current flowing through the diode. Right? If there's no current flowing through the diode, that means all the entire current of load IL must be equal to IQ. So that's why if you draw IQ, it's going to be flat at IL, right? And that happens until switch voltage is equal to Vs, right? So Vs is equal to VL plus VQ. Well, if VQ is equal to Vs, then that means VL is equal to 0, right? So at this point, at this point, VL is equal to 0. So when VL is equal to 0, that's when diode conducts. That's when current now can take over, or not take over, but takes turn. Now current goes down gradually, right, from the assumption. Okay, does it make sense why we have this transition? Okay, simply by applying KVL, KCL. Now, is that clear, or are there any questions on this? Okay, if not, then you might ask, why is it that voltage comes up first? Why not current? Why not current goes down first, right? Then voltage, right? So that's a valid question, right? Why is it that I'm drawing the switching trajectory? I'm drawing the switching waveform in such a way that voltage across the switch rises up first before current can come down. Why can't current comes down first and then voltage comes up, right? So let's see if that can actually happen, right? Well, let me erase this. Erase that. Let's assume that current comes down first, right? So let me use red. Right, so when it turns off, current comes down first. So this is IL, right? The whole thing is IQ, right? So switch current is what I'm drawing there with the red, and the flat line right there is IL, right? So as IL comes down, right, what's going to happen by KCL? What can you get from there? As IL comes down, not IL, sorry, as IQ, switch current. As the switch current, let me erase this. Right, hang on a sec. As the switch current right there start to decrease from IL, what does it imply? Anybody?
The diode.
Lower power.
No, by KCL.
Oh, by KCL.
Yeah.
More diode current.
Exactly. So by KCL, if IQ, current through the switch, start to come down from IL, that means the remaining current, right, because it's already lower than IL, right? That means by KCL, the remainder of IL must flow through the diode, yes? So I diode is not 0. You agree? Yes? Okay, let me know if you disagree, right? So that's the implication of IQ coming down first, right? As IQ decreases from IL, then I'm gonna have ID, non-zero amps through the diode. Okay, if that is the case, if ID is non-zero, what does that tell you in terms of VL?
Has to be 0.
Has to be 0. Very good. So as long as, right, I'm gonna use green now. As long as IQ is decreasing, right, voltage across the what now? Across VL, right, must be 0, right? If voltage across VL must be 0 to allow diode to conduct, therefore VQ must be what? By KVL.
BS.
BS. So if I draw voltage across the switch, it would still be not it would still be, but it will be VS right there, right? That's VS. Now, what happens before? So this is going to be true, right? It's going to be VS all the way. Not all the way, but as long as IL is decreasing. How do I do this? right there. Ah, that's not lined up. Right. So as long as IQ is decreasing, VQ, right there, that's VQ, must equal to VS, right? So this part right here, does that make sense, that part? Right. Tell me if you disagree, okay? All right, so hopefully that's clear to you. Again, if as long as IQ is decreasing, we have to have diode current flowing through the diode, which implies that diode voltage here should be equal to 0. If that is true, as long as IQ is decreasing, then VQ must be equal to VS. That's what I'm drawing right here. Right. So then what happens before the turn off transition? Before the turn off transition, what is voltage across the switch? Right here, for example, right here. What is the voltage? What is voltage across the switch?
Is it 0?
It's 0, right? Because the switch is conducting, just like this, just like that one right there. See, when the switch is conducting, its voltage is 0, right? So now I'm going to draw that, right? Right before that point, right before this point, switch is 0. So right at that point, when current through the switch start to come down, voltage across the switch is 0. And then as soon as the switch turns off, right, current through the switch goes down, and in order to accommodate for the diode current, voltage across the switch must jump to VS, like that. Make sense? Does that make sense? Or any question on that one? No? Make sure you understand this part. Yes or no? Any questions? You gotta let me know.
I think I got it.
Yeah. Oh, you have a question. One of you have a question. What is it?
Yeah. I get how the circuit works, but how does IL represent the load? That's the load, I'm assuming, right? The current source?
Yeah. It's just representing inductor current, heavily inductive. Right? If it's heavily inductive, then basically you have a constant current, right, with a small ripple.
Okay.
Right. How about the shape of the voltage there? Is it good, Nick?
Yeah.
Okay. Now you know why voltage has to come up first, not current. Because if you do current that goes down first, then what happens? Then voltage has to jump from 0 to VS, and that's not following the assumption, right? The assumption is that both voltage and current must change linearly, and also this is not practical, right? This is not realistic. This is not realistic, right? Voltage cannot jump right away, right? So that's the reason why. Hopefully now you understand why in my drawing right here, voltage is the one that comes up first, then current, instead of the opposite. If it's the opposite, then you get this picture right here. Okay. Any question on that? No? All right. I'm going to erase this, okay, so that I can use it again for explaining other things. All right. So now, if you agree with this switching waveform, right, this one right here, right, and not this one, not the one I'm going to erase, right. This is not true, right? This is not realistic, right? Voltage cannot jump instantaneously right there, right there. So, okay, if you agree with that switching waveforms for voltage and current of the switch, now we see the problem. Remember earlier I said, in order to, before we talk about snubber, we need to know the problem first before we talk about the solution, right? Before we understand why snubber is needed. So that is the problem right there, right? If you agree with, again, these, let me erase the whole thing here. Sorry, take some time to do this. So if you agree with this transition, then you can see there is a problem there. What is the problem? It's important to understand the problem before you can talk about the solution. What is the problem there? Don't read my notes. The answer is
voltage and current are high at the same time, which gives you power.
Exactly, very good. So just by inspection, number one, we have a problem because the two overlaps. IQ and VQ, they overlap. Anytime voltage across the switch and current through the switch overlap, that means we have switching loss, right? That's number one problem. Number two, was it Nick who said that earlier? And the other problem,
yeah.
Yes, thank you, Nick. The other problem is that, just like Nick said, is that this particular transition causes both peak current and peak voltage to coincide, right? Right there. Right? They occur at the same time. I should say there is a time when both voltage across the switch and current through the switch are at their max values, right? Why is that bad? Because that would give you P max. That would give you the maximum instantaneous power for the overlap, right? Very good. So now we understand the problems, right? Those two problems. Okay, now let's talk about solution. Don't worry about snubber first, right? You see the problem in front of you, just focus on the turn off, all right? Now, in what ways, don't look at my notes, okay? Don't read my notes, don't read the book. In what ways can we solve this problem? How do we minimize this switching loss? There should be two ways, at least. What's the first one?
Make sure voltage goes up later or current goes down earlier.
Ah, yes. That's right. That's right. So, yeah, I think you answer both ways, in my opinion. So the first way, right? The first way is to, let's say I'm able to slow down the rate of rise of this voltage right here. Let's say that instead of going that fast, what if I can slow it down? Let's say with a different slope. Let's say that slope right there, right? Let's just see. Then what's going to happen there if I'm able to do that? What's going to happen?
Your peak power is less.
Right. So you can see the overlapping is less, and then we avoid having the two peaks coincide, right? That's the first method of solving this problem, is by slowing down the rate of rise of the voltage across the switch when it's turning off. Is that clear? That's the first method. The second method is, what if I'm able to do the following? What if, right, I'm able to have this current through the switch to also change as soon as the voltage changes. So as soon as the voltage is rising, if I could somehow make the current also changes at the same time. See that? So at the same time, right here, current comes down. As soon as voltage goes up, current comes down at the same time. If I do that, notice that I'm also preventing the two peaks to occur at the same time, right? You agree with that assessment? Yes?
Yeah.
Okay. So now you know the two methods of minimizing switching losses, or in this case, turn off. Number one, by slowing down the rate of the rise of the voltage across the switch as it's turning off. Number two, by allowing current through the switch to also change while the voltage across the switch is changing, right? Now, what's good about snubber is that snubber circuit provides both, right? It can actually provide both the slowing down of the rate of the voltage across the switch, as well as providing alternate path for the current through the switch, so that you can actually change, current can actually change as soon as voltage changes, right? So that's the solution, right? That we should be able to do this if we can come up with the circuit that does both, either or both, but luckily snubber can do both, right? So these are the two solutions, okay? Once you understand the problems, then these are the two solutions that I just discussed with you. So what kind of circuit can do this? Right here, right? So I'm going to discuss what we call RCD snubber. Right? The reason being, well, the snubber circuit, that's the additional circuit right here, consists of 3 additional components: resistor, capacitor, and a diode. Right? Is there a different type of snubber? Absolutely. Right, but let's just look at RCD snubber first, right? And you can see that it is an additional circuit, right? That we connect across the switch, right? Look at how the diode is facing downward, and then we have capacitor, and then we have the resistor, right? So we have the snubber diode, snubber capacitor, and snubber resistor, right? How does this help? Well, number one, you can see by adding a circuit around the switch, you are actually adding another path. See that? Go ahead and do KCL now on this node. What was it before? Before it was IL equals to IQ plus ID. Now I have another path. Now I have plus I snubber right there, right? And this is good, right? This is an additional path that is good to have, as you will see later, because then it allows current through the switch to change as soon as voltage changes when it's turning off, right? Let's just go straight to that part right here. When the switch is turning off, right? We're gonna assume that when the switch is conducting right here, switch is conducting right here, this capacitor is already being discharged. It has to be, right? That's one requirement, is that before you turn off the switch, this capacitor, snubber capacitor, has to be fully discharged. So no more voltage, right? It's going to be 0 volts. Okay, and then we are turning off the switch. Right? Now we're going to turn off that switch. That's the picture right here, right? When the switch is turning off, right here, right? You can see that yes, that this diode voltage is still positive, so no current through this diode. But now look, right? Before, whenever this diode is reverse bias, right? You're not going to be able to allow any current flowing through it, right? So therefore, the entire current must flow to the switch. That's why you have that flat line, right? Earlier, when the voltage goes up, when the switch voltage goes up, remember earlier, the current has to stay at IL, right? That's the previous case. Has to stay at IL until voltage reaches Vs. Now is no longer true, right? Once voltage goes up, right, as you are turning off the switch, you're turning off this transistor, this node right there goes up, right, from 0 and gradually increasing, following a linear curve, right? As this voltage from here to ground, let me erase, right? As this voltage is rising, right? Look at what happened with the diode. Remember, this is 0 volt, right? So that node is the same as this node, right? So as this node is rising, so is this node right there, right? And you can see that by increasing the voltage at that node, you are also forcing the diode to To do what when this is 0 volt across? To what? Anybody?
Oh, Professor?
Yeah.
I have kind of just like a side shorter question about like the diode.
Mm-hmm.
Like in practical power diodes, how low can they get the forward voltage drop? Because like in this, we're assuming it was like 0. Like how low could they actually get it?
Well, this is not a power diode, right? This is a small diode. Doesn't take much energy. So you could get a diode that has, 0.1, 0.2 type of drops, very small.
Oh, so it doesn't have to handle a crazy amount of power.
Nope, it should not. If it is, then there's something wrong with the circuit, right? The only current that is going to be carried by this diode is what's called charging current. And the charging currents will be small.
But if you're just redirecting it away from a power spike from the switch, like would a switch just generally have a greater voltage? Like it's adding efficiency to the circuit, but it's just redirecting the same current though. So would like the MOSFET or the BJT or whatever like have a significantly higher voltage if we didn't have the snubber, or
higher voltage?
Like because we're saving power by adding the snubber, but like we're redirecting the same current that would have otherwise just gone through the switch.
Mm-hmm.
So the thing that I'm kind of confused about is like in order for like the diode to be a more efficient solution, it would have to be pretty significant less voltage.
What diode?
Oh, I guess never mind. I just answered my own question. I guess when the switch is like we're worried about when the switch is like half conducting, so it would have a bigger yeah. I got it.
Okay. Yeah. So this happens really fast. Okay. It's not like with respect to the duty cycle, this whole transition should be fast, right? So the amount of current that is being being accommodated by this diode is going to be tiny before the entire current flows through this big diode. So this is a big diode. That's a power diode. So it only requires a small amount of current to make the voltage rise across the switch slower, right? That's a charging voltage, a charging current, basically, right? And it happens fast that that before it's reaching, big current is already been delivered to the load up there, right? So I'm not sure if that addressing your question, but again,
no, it does. It's a low average because it's just a small little pulse every cycle versus
that's correct. Right, and it happens again only during that transition time. Okay, very fast switching transition. Okay, so that's why it's small current. All right. So now I think my question was, what happens as this voltage across the switch is rising? Well, the voltage across this branch will also have to rise, right? Because they're in parallel. As you can see, these two branches are in parallel. So as voltage across Q, the switch is increasing, so is the voltage from here to here, right? And remember, this is 0 volts because it's still not charged when you first turn off the switch. So now, by forcing this node to increase gradually, you are forcing this diode to turn on, right? Because this is 0 volts again right here, right? So as the switch voltage goes up to 1 volt, for example, this is increasing. This is going to be increasing as well to 1 volt. But this capacitor now is going to be slowly charging because this is forward bias, right? So now by gradually increasing the switch voltage at the same time, you are forward biasing the diode, and in the process, you are charging the capacitor right there.
So essentially, like the switch voltage is changing at the value of the capacitor times the load current? Because it's just redirect. It's CD or I is equal to CD. Oh, current divided by the capacitance.
Yeah, so VC is equal to 1 over C, integral IC dt. We'll talk about the equation, maybe not today, maybe on next time, but yes, you're right. So it's going to follow that equation, right? Following that current, you're going to charge that capacitor based on how much current is flowing through that cap, right? And in the process, you are slowing down because again, these are in parallel. Right now, just assume this is 0 volt. Okay, when it's conducting, to make it easy, when it's conducting, the diode is 0 volt. So as this voltage now rising, right? So does this voltage. So is that voltage, right? So now, since the two are in parallel, by connecting this diode capacitor pair across the switch, you are slowing down the rate of rise of this voltage rise across that switch, right? So before it was fast, now it has to slow down, right? Now it's going to be slower because of that capacitor. Of course, the bigger the capacitor, the slower it goes up, right? Right, that voltage across the switch. Does that make sense first?
Yeah, all good.
Okay. All right. Again, that is possible because we are allowing current to go through another path, right here. That's another path. So now we're allowing current to charge that cap. Before, there is no path there, right? You just have a switch, an inductor, and a diode. But now we do. Okay. Now erase this. So now you can see why I use these thick dash lines to show you how current flows when the switch is turning off. Okay, and this happens until, of course, until this voltage is reaching Vs, right? Because this is 0 volt across the diode. That voltage is the same as that voltage, Vs, and that's also Vs right here. Eventually, it's going to reach Vs, right? But the time to reach Vs is going to depend on the size of that capacitance, right? As well as how high is Vs, of course, right? For the same capacitance, if Vs is larger, then it'll take more time, of course, right, to reach Vs. Okay, any questions? So what about current, right? We know that voltage is now slowed down, right? It's now being forced to slow down because of that capacitor. What about current? Can current changes as voltage changes? Yes, right. Exactly, that's what's happening, right? As soon as this voltage rises, right, you are right away forward biasing this diode, and right away you are charging this cap, right? So by rising this voltage, as soon as this voltage rises, you are forcing current to go this way. That's now you have two currents. You see that? Right there. So that means current can also change. This is IQ and this is VQ, right? So as VQ goes up, IQ can go down at the same time, right? The remaining current goes through the capacitor to charge capacitor. Is that cool? Right, so that Snubber provides the two solutions that we are looking for. Number one, slowing down the voltage rise across the across the switch. And number two, adding a path so that current through the switch can change as soon as voltage across the switch changes during turn off. Okay, so then if that's clear to you, any question before I proceed? All right, so then that happens, right, during the turn off switching, and then at the end of the transition, right here, not right there, but the end of transition, once the turning off is done, then this capacitor will have Vs, as I said earlier, right? So now it's fully charged. And then what happens when the switch turns on? When the switch turns on, we want to discharge this capacitor, right? So on the right-hand side right here, that's when the switch is on. When the switch is conducting, right, we want to make sure that this capacitor is fully discharged through resistor right there. Right? So fully discharged through the resistor and goes through the transistor that way, right? And we want to make sure that this capacitor is fully discharged before you turn off the switch again, because otherwise, you know, you're going to have a capacitor voltage that keeps increasing and increasing until the capacitor blows or the switch blows, right? So again, you want to make sure that that happens. How? Well, we're going to look at the equations to be able to properly size this resistor and capacitor. All good? Any questions so far? Yes, no? Still good? No, gotta let me know. Any questions at all?
I had a quick question. It's kind of a continuation of that current through the smaller diode DS.
Mm-hmm.
Does the current through DS approach the current going through the switch, but only happens like instantaneously, so it's not a problem?
I don't think so, because you know we just need a fraction of time to do this.
Mm-hmm.
So before IQ finishes, you can have you know, diode takes over, right? Again, this is happening very quickly, right? Only during switching transition. So with respect to the duty cycle, this is very tiny. This is very short time, very quick.
Okay.
Okay.
Thank you.
All right. Mm-hmm. Any other questions? Okay, if not, let's look at the effect of this snubber, right? So this is before snubber, right? That's what happens before snubber. Current right there stays flat while voltage goes up, and then current start to come down when voltage is done, right? Voltage reaches Vs, right? And you can see the overlap, right? And if you do instantaneous power, V times I, you're going to end up with a PQ instantaneous power waveform that is a triangle, right? From which it's easy to find the area, right? The switching loss. That's what happens before snubber. After snubber, remember what we want to do? We want to avoid having this peak, right? And we want to minimize the overlap. Take a look at what happens after snubber, right? So as soon as voltage goes up, current goes down at the same time, right? By doing so, look, the intersection, right? Intersection, yeah. The intersection is not at the peak values anymore. So this peak will be less than the peak before, at the peak of the triangle, right? Now notice that if you do V times I, the overlapping is minimized also. Look at V times I, it's no longer triangular wave, right? Why not? Well, because we have two linear functions, right? We have a linear function for current right there, and another linear function for the voltage right there. So if you multiply a linear function times a linear function, it's not going to give you a nice, you know, line, right? A nice, you know, linear function, right? You're going to have some a quadratic equation because of this, right? So in terms of calculating switching loss by adding snubber, it's going to be a bit more challenging than finding switching loss before snubber. I just want to give you a heads up on that one. Right? Now, also another thing is the timing here, right? You can see that I could adjust how long this voltage across the switch reaches Vs, right? And I put Vc there, voltage across capacitor, because that's equal to the voltage across Q. They're in parallel, right? So the duration of the time, how long it takes for voltage across the switch to reach Vs, can be adjusted by sizing the capacitance, right? Larger capacitance will give you even slower time to reach Vs. And take a look at what happens if I use larger capacitance. See that it's even slower rise, and you can see the overlap is even less, and the peak is even less as well, right? So by increasing the snubber capacitance, you can see the two areas there. Hopefully, you can see that the switching loss becomes less and less. Okay, so that's the effect of increasing the snubber capacitance. Any question on that one? So then my question is, if that is the case, why can't we just use big capacitor, right? If I use big capacitor, then theoretically speaking, right, like a big one like that, then right, the amount of overlap is even very small, right, to the point that is negligible. So why not? Why not just put a big capacitor?
That will interfere with the frequency of switching.
Very good, very good. Keep in mind that we are taking away. There's always a trade-off, right? Something has to give. By increasing the switching time, that's basically increasing the switching time, right? The transition time. You are taking away some time from the duty cycle. So now your duty cycle is going to be more limited by increasing the capacitance. The other reason, a bigger reason, is something that we have to look at the mathematical equation. We'll do that maybe next time. Is that don't forget that as soon as you are charging that capacitor, right, you are also storing energy in that capacitor. Do you agree? Yes?
Yes.
How much energy do we store in that capacitor? What's the
1/2
equation?
CV squared.
1/2 CV squared, exactly. 1/2 CV squared. And guess where that energy has to be transferred to?
A
Resistor.
resistor, right?
Exactly. See this right there?
Which is just heat.
See that? So that's the implication, right? Is that by having a lot of big capacitance, you are storing more energy into that capacitor. That energy, unfortunately, has to be flowing through these, will be used by this resistor, and in turn is translated into power loss, right? So the power loss on that resistor is 1/2 CV squared times F. Energy is 1/2 CV squared, right? That energy flows, or not flows, but it's being used by this resistor, and in turn translated into heat. And the amount of watts corresponding to that stored energy is 1/2 CV squared times F, right? Remember I said earlier about being careful when sizing these numbers, right? If you're not careful, then the entire loss, even though the switching loss is minimized, even though this loss is reduced, but the entire converter loss could be higher if you're not careful on sizing this capacitance, all right? You see the problem there, hopefully, right? So then how do we pick proper sizes of these components, capacitor and resistor? Well, this is where we have to use mathematical equations, right? So math is our friend here. And so by looking at mathematical equation, we can then do the analysis, and then we should be able to determine what would be the good size for this cap and the resistor, right? Okay, oh gosh. What is the next page? Before I go there, I almost forgot to do the following. Look at the timing first, Tx and Tf, right? Because we're gonna have to derive the equations for voltage across. We have to determine the equation for voltage across the switch, and then current through the switch, as well as voltage across the cap, right? In order to do that, we need to know what these times mean. So TX, sorry, TF right there. TF is the time it takes for the current through the switch to reach 0. Right, that's TF. TX is the time it takes for the voltage to reach its final value. So that's TX right there. Right, so you have TF and TX, right? And you could see that one criterion to select the proper sizing of the capacitor could be that we want current through the switch to reach 0 before voltage across the switch reaches its final value, right? Because if you do that, then we have small amount of overlap, right? So basically this, right? As long as TX is less than or equal to TF, oh no, the other way around. As long as TF is less than TX, then we're good, right? Because if what happens if we do the opposite? What happens if TX is less than TF? What's going to happen? Why is it not desirable? Anybody? Imagine this point, you move it to here, right? So you have big overlaps, right? Basically, right? So so the maybe the better, not the better, maybe one of the a good criterion to use to minimize overlap, to quantify, right, how to minimize overlap is by using these two timings, right, these two times. So that's to minimize the overlap, let's target our TF to be less than or equal to TX. Does that make sense? Hopefully. Okay, because that's the question, right? How do you minimize the loss? So now we can start quantifying that by using these timings. Any questions? No? Okay, if not, let's move on. Okay, let's derive the equations, right? In order to size the capacitance, I need to know capacitor voltage, right? Because that's basically what, let me go back, sorry. Right here, let me erase all of these. Remember that VC is equal to VQ, right? And so if you want, I already erased it. If you want TF to be less than TX, less than or equal to TX, then notice that when we have TF, when IQ reaches TF right there, you can see that that corresponds to a certain voltage level across the cap, right? That's what I call VF. See that? So at that point, you can see that point, that voltage right there is called VF, is the voltage at which we have time equals to TF, right? So voltage across the cap at TF, right? And so how do we, again, design the proper snubber? By looking at specifically voltage across the cap when current is already done, right? When current reaches 0, right? So this could be a voltage that you could assign, some voltage, whatever that is, right? Has to be less than supply voltage, of course. Let's say that voltage, call it VF. That's our target right there, right? The less VF, imagine if VF is less, the bigger the capacitance, right? The less the VF, the bigger the capacitance. Sometimes you can also pick VF to be equal to VS, in which case you have the first picture right there, right here. Right? That's the case where VF is equal to VS. So far, so good? Yes? Right, so again, this is equal to VC at TF. So you can see that in order to quantify this, right, the mathematical equation that we need is VC, voltage across capacitor, right? And as you learn from circuits, in order to get voltage across the cap, you need current through the cap, right? VC is equal to 1 over C, integral from 0 to T, IC dt plus initial condition, right? So that's what we're going to do, right? In order to get VC, I need IC first. What is IC equal to? Well, take a look at the circuit. Oh my God. It always does that. Okay. Look at IC. Well, that's current through the capacitor. Okay, right there. What is IC equal to? Here's IC. Right, you can see that by KCL, IC is equal to IL minus IQ. Right, there's IL minus IQ. Right, should be equal to I capacitor. So that's what I'm gonna do next. Okay, let's go through the equation right here. So I need IL is given typically, right? That's load current. I don't know what IQ is, so I need to know IQ first. What is the equation for the current through the switch? Can you do that? Yeah, because it's linear function, right? Let's go back. What is IQ equal to? Come on, right here. So let's erase this. Erase this. Okay, focus on this. Focus on this equation right there. Right, this. What is the equation for that one? Right, assuming this is t0 equals to 0, right? What is the equation that describes that linear function right there? Well, you should know that's a linear equation, right? With a slope, with a negative slope, right? And then length of time is TF, right? So y again, just that straight line right here, right? Y is equal to mx plus c, right? And we know that in this case, current IQ is equal to, instead of x, it's actually time. So what is the constant there? The constant is IQ, right? So plus IQ, oh, not IQ, sorry, IL. That flat line is IL. What is the slope? What goes into this? Well, you know the slope is dy over dt, right? What is dy? Dy is 0 minus IL. dt is TF minus 0. You agree? So therefore, the slope there is minus IL over TF, right there. So therefore, the equation that describes that line, the linear function should be I of QT is equal to M. What is our M again? Minus IL over TF T plus IL. Do you agree with this? Any question on that one? And that should be the equation I have for IQ, right? That happens, that's only true before TF, from 0 to TF. After TF should be 0, right? So let's see if that's what I have. Right? Come on. Okay. Right there. See, IQ from 0 to TF is equal to, what did I say earlier? I of QT is equal to, oh, what was it again? Minus IL over TF, T plus IL, right? So you can carry out the IL, and what do you have there? 1 minus T over TF. Isn't that the same as this? Right. So that is true from 0 to TF. Any question on that one? And then we know that after TF, the current through the switch is 0. Right, so that's easy. So why it is important to know IQ? Well, because we know by KCL, IC is equal to IL minus IQ of T. Right? So go ahead and plug in this equation into here. You should get that equation right there. Again, only true from 0 to T to TF. Right? Okay. And then the rest should be what you get there. Any questions? So I'm only interested in this the switching transition right there. Okay. So now that I know the equation for IC, what happened with voltage? Because that's eventually that's what I want, right? I want to get equation for the capacitor at TF. Right? That's our criterion, right? And in order to get that, I need the equation for VC of T. Right? How do you get the equation for VC of T? Right here, right? 1 over C, 0 to T, IL over TF, T dt, IL T square. Oh, sorry. This is IC. This is my IC right there. Right? Is that true? From 0 to TF? Right there, right? From 0 to TF, that's the equation for IC. And that's what I have. That's what I put under the integral. Right? Right there, as you can see. And yeah, and then I carry out the integral and I get the equation that I need right there. And that's what I need to do for this one. That should be enough equation for us to see. Right now I have the equation for VC of T. Right now, once you get the equation for VC of T, what is next? Notice that if you just focus on this set of the equation right there, right, which is true only for this condition. Notice that capacitor voltage is a function of capacitor right there. Right, that's good to have because then I could size the capacitance based on this equation. Right, so that's what I'm going to focus on. VC of T is equal to IL T square over 2C times TF. Right, now if I plug in TF, this equation becomes what? Becomes this equation right here. So when T is equal to TF, that equation simplifies to this equation right here. And then you can simplify even further because one of the TF cancels, you get this equation right there. Right? So now, again, keep in mind that the criterion is that I want to specify how fast that capacitor voltage rises, right? By determining this voltage right there. Let's call it VF. So you have to provide VF. That's known, right? That's given. So once that's given, now we already have the equation for VC, which is right here, right? And at TF, sorry, not that, so the previous equation, once you have the equation for VC, go ahead and plug in TF into that equation, and you get this equation, right? And set it to equal to VF, right? Because that's equal to VC of TF. Does that make sense? This is given, or this is known. And you can see that IL is typically known as well. That's the maximum current, right? As average current through the load. TF is typically something that you can get from, not you get, sorry. That's the fall. What is that TF? Oh yeah, that's the fall time of the current through the switch, right? So that's something that you can typically get from data sheet, right there. Right? So the only thing that's unknown is C. So then you can solve for C, and that's what you get, equation for finding C. Right? So now we have the equation to size capacitance. That capacitance for the snubber should follow this equation. The only thing is you need to provide VF. How much voltage you want across the cap when the current through the switch is reaching 0. Right, that's TF. Again, TF is typically provided in the data sheet of a a switch. It's called a fall time. Okay, any question on this? Okay, sometimes you want VF to be equal to VS. If that's the case, go ahead and plug in VF equal to VS. If that's the case, that equation now becomes this equation. Again, this is only true if VF is equal to VS, right? VS, which implies that TF is equal to TX, right? Any questions on this? Okay. How about resistor? How do you size a snubber resistor? Now that you know the equation to size capacitance. Okay, capacitance value. We have not talked about the limit for this capacitance, right? This is just the capacitance value that you can calculate for snubber circuits. Later on, not today, maybe you'll know, you have to know the limit of this capacitance. Like we discussed earlier, we cannot just keep increasing capacitance value, right? Because then you're going to end up with a lot of loss. So maybe next time we'll talk about the equation for that. But let's finish the R value, right? Because we have R, C, and D, right? What about the R value? Well, remember that I said that when the switch is on, we want to be able to discharge this capacitor, fully discharge this capacitor, so that when the switch is turning off again, you should not have any voltage or charge left in that capacitance, right? So that has to do with time constant of the capacitor. Because remember, when the switch is on, the capacitor discharges through R, right? Remember that circuit that I showed earlier, right? When the switch is on, right there, this capacitor discharges through R, right? So now we have RC time constant. So you want to make sure that the RC time constant is going to be much less than the on time of the switch. Or in other words, the on time of the switch must be larger than the time constant of the RC circuit that you have here. So to be on the safe side, I'm going to put 5. Right? This is kind of random. Usually people pick 3 to 5. I'm just going to put the worst case, best case, I should say, 5 times RC. Right? So 5 times the time constant to ensure that the next time this switch is turning off, there's no more charge left in that capacitor, right? So again, this 5 is something that you can pick, but for this one, I'm going to use 3. Oh, sorry, 5. Man, sorry about that. 5. So the on time of the switch, as you learned from PWM, ideally is equal to D times T, right? That's duty cycle times the period, ideally, right? So therefore, I'm going to replace T on with DT, or DT is equal to D over F. So now if you plug in D over F into this equation back right here, then you get R, and then solve for R, then you get the equation for selecting R. That R has to be less than D over 5 CF. Of course, this constant 5 will change depending on how much time constant you want to allow to discharge. Any questions so far? So those are sizing values of the capacitor and resistor, right? Are there any questions? Let's see, I have 3 more minutes. I think I should be able to finish this. No more questions? All right, so those are just giving you equations to calculate resistance value and capacitance value. Those don't tell you, they don't tell you the entire design requirements though, okay? As I said earlier, there should be a limit on how much capacitance you want to introduce. And that relates to power loss, right? And so let's look at power loss before and after. This is the general equation for power loss on the switch, right? 1 over T, 0 to T, and then the instantaneous power of the switch dt. Okay, and then you can see that before snubber we have the triangular waveform, right? Remember the triangular waveform? That should be easy, right? 1/2 times the height times the base times F, right? Divided by T, but inverse of T is F. So that's why calculating switching loss before snubber is straightforward. It's just a area under the triangle divided by period or multiply by F. Any question on this one? That's before snubber. Again, that's the height, product of current and voltage, and that's the base of the triangle, TF plus TX. All right, after snubber is no longer simple because we don't have triangle anymore, right? Remember, you have linear equations. We already derived the equation for VQ and IQ, right? So right here, VQ, which is the same as VC. Don't forget that this is the same as VC. So we have the equation for VC of T and IQ of T. So go ahead and plug in those values. You know, the very first equation, remember we have range from 0 to TX, from 0 to TF. So go ahead and plug in those values, those equations, sorry, for VC and for IQ right there, right? You can see they are not linear equations, and you have to carry out the integral from 0 to TF, because that's the condition we have, right? TF has to be less than TX, and times F, and you get this equation right here at the end. See that? This is before, this is after, right? Take a look at what happens before, and then we can adjourn. If you look at the equation for power loss, switching loss after the snubber, you can see that both are still a function of F. That's not good, right? So as long as you increase switching frequency, you're going to increase the loss. However, when you do the snubber, you have the C right there in the denominator, which is good news, right? Because that means that if you increase C, if you have C value here, then you can get less and less power loss on the switch, right? So this is switching loss. Okay, so those are the two conclusions that I can get from these equations. Number one, before we adjourn, is that both equations, before and after snubber, they are still a function of switching frequency, just like regular PWM. And then after snubber, you can see that switch loss is inversely proportional to capacitance value. And I'm going to end it at that point.